Now for the fourth problem, we want to do a ring, same type of ring that we have here. So we're going to get the same expression, 2 pi r delta r, for the ring area. We're given the mass of the disk to be capital M and the radius to be capital R. So what we're going to do this time to get the mass of the ring is we're going to multiply its area by the mass per unit area for the ring. Mass per unit area is just mass divided by the area of the ring, and we assume the mass is uniformly distributed over the ring. So multiplying the ring area by the mass per unit area, we get our expression for the ring mass. Then what we want to do is we want to figure out the kinetic energy of the entire disk. So we partition our interval, our R interval, from 0 to big R, which represents, of course, the center to the outer rim of the large disk. And we partition that as 0, and I've got 0 less than R, it should be 0 equal R. 0 equal R naught, and then that's less than R1, less than R2, etc., etc. You've got an Ri in the middle here. I probably should have put an Ri minus 1 and an Ri in there. It's not incorrect, though. And we have Rn minus 1, Rn, and Rn equals big R. Now, some of it's kind of small, but I think you'll be able to see it. Here's our disk, and it has radius big R and mass big M. And we've got the interval from 0 to big R out here, and we got that broken up into little pieces. Now I don't have thousands of them or millions of them, but I've got a few pieces here, and I think you can see those markings. And then I'm not going to attempt to draw it because I've already got a pretty good circle there for a freehand circle. If I try to put a circle around the center, it's going to ruin it. Okay. But between any two of these points, we would have then a ring, okay? So any interval of this partition, these would be the intervals of our partition, and any interval would then correspond to a ring all the way around, thickness of the ring being the length of the interval, and the radius running from the lesser to the greater value of R. Okay, well, hopefully that's obvious to you, because if you've had a first-year calculus course, you've done this. And if you had a first-year calculus without having done this, something important was really, I'm afraid, left out. And you're going to have to hustle a little bit, maybe. Okay. So we've partitioned this interval, and we want to find the mass of the ith interval. Now, the first interval runs from R0 to R1. Second interval from R1 to R2. So the ith interval is going to run from R sub I minus 1 to R sub I. Okay, so the mass in that interval is going to be what? It's going to be 2 pi times R sub I star delta R, and that corresponds to this expression. That's the ring area for a typical ring. Except now I've got that R sub I star. What does that mean? Well, R sub I star is some R between R sub I minus 1 and R sub I. Remember, our ring goes from radius R sub I out to radius R sub I. I'm sorry. Our ring goes from radius R sub I minus 1 to radius R sub I. And R sub I star is just going to be a sample radius in between. So this is going to be what we take for our mass of the ith interval. Now we multiply that, of course, by our m over pi r squared. So we just have this expression, and the only difference is now we're talking about the ith interval, so r is going to be r sub I star again being some sample radius between ri minus 1 and ri, between the inner and outer radius. Okay, well, that's the mass of our ith interval. Now what we want is the kinetic energy, but I'm going to digress a bit. And I'm just going to calculate the total mass of this disk. Okay? Now, we already know the total mass, but let's do this by an integral and see if our integral agrees with what it has to agree with. Okay, so we sum up all these mass increments, okay, which means that we sum up, well, we're going to factor out the 2 pi m over pi r squared. Now the pi's divide out, so we get 2m over r squared. And then that's times our sum of our r sub I star delta r's. Okay, so if we add up all the mi's, every one of these has this common factor and has then r sub I star times delta r. And in the limit, as delta r approaches 0, our partition gets dense, and we get the integral from 0 to r, and I wrote the integral sign down there. Matter of fact, I'm going to change that. I'm getting tired of looking at it. Okay, so we approach 2m over r squared, and then this sum approaches the integral from 0 to big R. Because our partition goes from 0 to big R, our integral will go from 0 to big R of r dr. So now that integral is really easy. You just get r squared over 2. So when you multiply the r squared over 2, big R squared over 2, you get from this by the 2m over r squared here, everything divides out except the m. So what have we discovered? We've discovered that the mass of this disk is m. Of course, we were already given the fact that the mass of this disk was m, but this at least confirms the process that we use to derive the integral. Okay, we set up an integral for the mass, and it works out. So we know we're on the right track. Now we just have to do the integral. We have to adapt this a little bit to get the integral that gives us the kinetic energy. Okay, to get the kinetic energy of the ring, our typical ring, which will then be able to adapt to get the integral, we get the mass, of course, is just the same thing we had here. What's the velocity? Well, the velocity of the ring, we multiply our angular velocity by our radius to get how fast the mass in that ring is actually moving. So the velocity is just omega r. Okay, and omega is one of the quantities that we're assuming. So our kinetic energy contribution is 1/2 delta m times v squared, 1/2 of this mass contribution here, multiplied by the square of our velocity, and we then move that on into an integral. Now, for the typical interval, we'll have an r sub I, and we'll have the r sub I here as well. Okay, so our r sub I star here and here. That's going to give us an r sub I star cubed instead of just an r sub I star, so that when we do the integral, we're going to have an r cubed in the integral. And of course, we're going to have a dr because our delta r is going to approach at dr. And then everything else, well, the 1/2 divides the 2, goes away. Pi divides pi, that goes away. And we're just left with what? Omega squared here and m over r squared times r cubed dr. Now, again, should have factored this constant stuff out of the integral. And as a matter of fact, I'm going to rewrite it that way. So our total kinetic energy is going to be the m omega squared over r squared constant factor that we get out of all of our mass contributions times the integral from 0 to big R of r cubed dr. And that integral is easily calculated to be big R to the 4th over 4 multiplied by omega squared m over r squared. We get 1/4 omega squared times capital M capital R squared. Now, that's it. That's a good expression for our kinetic energy. But to kind of foreshadow where we're going with this, this is 1/2 of M capital R squared over 2 times omega squared. Now, why would I write it that way? Clearly, if I multiply this out, I get this, and that's fine. Well, this mr squared over 2 I'm going to call I. Now, you don't know why I did that, but it'll become clear. And we get 1/2 I omega squared. That's kind of analogous to 1/2 mv squared, with I equal to big M big R squared over 2. So kinetic energy is 1/2 I omega squared which is analogous to 1/2 mv squared. I acts sort of like a mass, except of course the mass is multiplied by the square of a velocity, and this I thing is multiplied by the square of an angular velocity. So there is a difference between the mass and this I thing here that we have. And that I thing is called the moment of inertia. That's a topic that we'll take up shortly.